Alright, so hello everyone. My name is Rodney Alone. I'm a PhD student at the Center for Research in Computer Vision at UCF. Today I'm going to be talking about the work I did together with Dr. Dong Zhang and Dr. Mubarak Shah, entitled ClusterNet, Detecting Small Objects in Large Scenes by Exploiting Spatio-Temporal Information, and this work is going to appear in CVPR 2018 in July. So if we look at the typical object detection problem, it's typically on the order of trying to detect 2 or 3 objects per image, and the objects tend to take up roughly 1/4 to 1/5 of the total size of that image. Okay, and you can see some examples here, right? So you can see the objects are relatively large, and there's usually only 2 or 3 of them, right? So for the Pascal VLC dataset, it's 2.3, for ImageNet it's 3, and they take up roughly, 1/5, up more towards 1/4 of the total image size. But if we start to look into a much more difficult problem for object detection, for example, if we look into WAMI data, which is wide area motion imagery, we're trying to solve object detection on the scales of several thousand objects per image, where the object size is roughly 0.0000007% of the total image size. So what does this look like? It looks like this. We have giant frames in comparison to what we typically work with in object detection. So this is 6 overlapping cameras forming a single sensor. It covers 19 square kilometers of area. Video frame rate's about 1.25 frames per second, whereas typical frame rates anywhere on the order of like 30 frames per second up to 60 frames per second, somewhere in that range. It's single channel video, so we don't have color. There's over 315 million pixels per frame, and the average vehicle size is only about 9/18 of those pixels. So very small objects, very large scenes. A couple more facts. It's about 2.4 million vehicle detections over 1,000 frames, which averages out to well over 2,000, in this case, vehicles that we're trying to detect in these video frames. So what does that look like? So as I said, there's over 2,000 vehicles we're trying to find in this. If we want, say, a deep learning algorithm or something to try and find all of them, I don't know if you guys can find them all right now in the room, but picking them out is pretty tough. So here, we'll blow up a small section. So this yellow section is enlarged. And I don't know if everyone in the room in the back can see these red dots, maybe. We'll blow it up one more time. So here's a blue section that's enlarged. So this is the goal. This should be the output of our algorithm, is it should take in this, or a section of this, and output these red dots. Okay, so a little bit different scale problem than typical object detection works with. There's a lot of other difficulties too. As I mentioned, the low frame rate. So you can see this red X, which is much larger than the vehicles we're trying to detect, moves significantly from one frame to the next. So when you're trying to look at changes over time, the pixels move so that they're completely not even remotely near each other from one frame to the next, which makes doing things like optical flow and things like that very challenging. Because the cameras are moving, when we stabilize the frames across time, when we compensate for the motion of the camera platform, you get these motion parallax effects, where we can see in the bottom, here's a row of vehicles that we probably are interested in, we're trying to find, but at a later point in time, the building has more or less tilted and completely covered that entire row of cars. So it's gone, but we want our algorithm to still hopefully try and find these, right? Given a series of video. Things like mosaic seams, blurred and unclear object boundaries, and dramatic differences in camera gain, which cause dramatic illumination differences. Illumination differences really cause a problem when you start talking about things like frame differencing or background subtraction, where a constant global illumination is really needed to give you a consistent pixel intensities across time. So here's our proposed framework. This is our proposed solution to this problem. We're using a 2-stage convolutional neural network, which I've called ClusterNet and FoveaNet. What ClusterNet does is ClusterNet takes in a large area of frames. So we have some height, some width, and some number of frames that we're inputting to a deep convolutional neural network. These frames are downsampled dramatically early in the network, and we're doing some processing on them with, you know, a CNN, typical CNN that you guys I'm sure have seen before. And our output here is the areas of interest that we think vehicles may be located. Because of the dramatic downsampling, the precision here, the localization ability of the network is extremely low. Right? We can only say to a very rough degree where we think vehicles may be located. And within each of these output pixels, these output neurons of the final layer of our cluster network, there can be anywhere from 1 to over 300 vehicles within the receptive field of that output neuron. And if there's any amount of vehicles in there, 1, 10, 50, 100, 200, we want it to give us a high value and says, hey, there's probably a vehicle here, you should look at it. We then take these regions that are high scoring in the output of ClusterNet, we follow the effective receptive field of that high scoring neuron or high scoring set of neurons. We follow it back through the network and we grab the associated region of the input space. So that's what it is here. RFH, RFW is the height and width of the effective receptive field of those neurons, because what happens is the receptive field is what of the input space that neuron gets to see, and we know anywhere within what it gets to see, it's saying, hey, there's a vehicle. Right? So perfect. And we want to grab all the frames because we're trying to exploit temporal information. I'll talk about that a little bit more later, how that all comes into it. And we send this through another CNN, and this one is doing the fine-grained localization. Right? So here in this region, what was a blur, now we have individual localized objects. So we'll walk through an example of what that actually looks like to make it much more clear. So here's a big area, right? Lots of trees, lots of obstructions. The output of ClusterNet from these set of, in this case we're using 5 frames, are these areas here, right? These are the high scoring areas. So you can imagine what we ended up choosing to do, and you could do this slightly differently if you want, but what we ended up choosing to do was place a grid over the output of ClusterNet in 4x4 pixel regions, and each of the grid cells that was scored above some threshold, we said we'll check those regions. So with the grid of 4x4 pixels over this output gives us 324 possible grid cells that we might want to check. And we only have to check 9 of those 324 possible because of the use of this first stage of the network. We then, as I said, follow back up the receptive fields and check those areas. And as you can see here, an example, right? There's a car here, 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 and those are showing up here. And there's actually one right at the edge here too that it's actually picking up. Any regions that we said not to check are automatically filled with zeros. Any regions that we did check are filled in, and then any overlapping regions are just averaged. And that gives us our final output. And as you can see for this example, we have perfect precision and recall. We got every single vehicle with the R predictions labeled with the green, yellow dots, and the red circles are the ground truth. Results. One quick note to make here is that, as you can see, if we're using a set of frames and we're making a single prediction, we have to have some sort of ground truth for our network, right? So our ground truth is the temporally center frame of the set of frames. So if we're using 3, it's the second frame. If we're using 5, it's the third frame. Okay? And what that allows our network to do is, instead of just giving it a single frame and trying to say where are the objects, we're now saying, well, let's give you some neighboring information, and hopefully that neighboring information will allow you to figure out what we want in the frame that we actually care about. And then we can just walk through time, keep giving it this little window of information, and it ends up giving us some really great results. So we'll see here what happens when we try some other approaches. So first we looked at FastRCNN. FastRCNN is extremely popular. It's very successful in object detection. Unfortunately, the results are very poor in this very challenging data set. This was consistent with what a lot of other recent works in literature have reported, that this challenging data, this whammy data, is extremely difficult for standard learning, machine learning based algorithms to sort of tackle. We looked at combining background subtraction with deep learning, and that's this blue curve over here. The idea here was background subtraction is the state of the art right now for object detection in whammy data. Okay, it's very successful. The difficulty is there's a lot of false positives associated with background subtraction that come from those motion parallax effects, the illumination changes, things like that. So if we can combine that with deep learning, maybe we can, remove a lot of those false positives and get much better results. And we did. But then we said, well, it's kind of a pain to go through and calculate all of the median images, calculate all the background subtracted images, and we have all this computational overhead. What if we can just get rid of that? What if we just get rid of the background subtraction and do, as I said, the proposed approach of inserting multiple frames to a CNN, and let's see what the results look like there. We'll go back to that one. And as you can see here, the 5-frame heat map based curve is pretty much identical to the background subtraction plus deep learning curve, which seems to imply to us that the network is, if not learning a sort of pseudo background subtraction, it's at least able to perform on par with a background subtraction approach. So we no longer need that computational overhead of computing everything ahead of time. We can just give the raw frames to the network and let the network do the processing. If we give it less frames, so if we only give it a single frame versus 3 frames versus 5 frames, we observed going beyond that to 7 frames, 9 frames, there was no improvement over 5. So we just left those off. We stopped at 5 frames. And here's the final results. We compared against 13 other state-of-the-art methods, all doing things like frame differencing with some stuff on top of it, 2-frame, 3-frame differencing, and background subtraction with a bunch of different things on top of it. Our curves are shown in the yellow stars and the blue diamonds. And as you can see from the precision recall curves, we're significantly above the literature right now, which was very exciting to see. The difference between the blue and yellow curves here is one of them is performing a heat map based approach where we're doing from 0 to 55, and we're using a mean squared error to sort of localize, or if you want to call it regress, the values of the heat map. We also looked at another approach where we do a sort of binary segmentation, so it's just 0 and 1 instead of 0 to 255, and we're using a cross entropy loss to try and figure out where the vehicles are. Both of these performed pretty identical to each other. Some were better in some cases, some were better in other cases, but the results were very comparable. These are the 13 state-of-the-art approaches we are comparing with, and these are different areas that are cropped out from the Wright-Patterson Air Force Base 2009 dataset. This one here is significant, this bottom row, right column, because what they're doing is persistent detections, meaning all of these other approaches, when a vehicle slows and comes to a stop, that vehicle is no longer considered in the ground truth. They're not trying to detect it anymore. And the reason they do that is because with background subtraction and frame differencing, you are unable to detect stopped vehicles, right? If nothing's moving and you're doing frame differencing, it's identical to the background. It can only pick up things that are moving relative to the background. Okay, so they don't compare with moving objects. This approach here is keeping all of the objects in the ground truth. So they're trying to do persistent detection, and they're using a tracking algorithm to sort of keep track of the objects when they come to a stop. And here's our proposed method, and here's the results you see in the bottom column. And again, these results are consistent with graphs. We're doing very well. Some quantitative results, or excuse me, some qualitative results. Here's the quantitative results. And again, the red circles are the ground truth, and the green-yellow dots are our predictions of the network. Another interesting example is, as I said, we're dealing with stopped vehicles, and as you saw from the chart 1 or 2 slides ago, we're doing very well at that, right? We're at 92.7%. So here's an example. Here's some cars stopped at a drive-through, and here's our results on these cars. So as you can see, this car pulls up. It's this bottom one here. There's actually a vehicle right here that's about to pull away in a second. There it is. And as you saw, while these vehicles are stopped, we maintain detection the whole time. Right, so this is very exciting. This is the first time people are doing very well at maintaining detections of stopped vehicles without doing some sort of tracking algorithm on top of it to not lose them when they stop. Cool, so that is everything. Thank you guys for listening to my presentation.